Hey guys, welcome to the next video on stereochemistry. This one is going to be dealing with enantiomers and diastereomers, and in the next video after this we'll be talking about meso compounds. Okay, so we already went through Rns configurations, and that's going to help us when we're talking about enantiomers and diastereomers, right? So let's define what these terms are. All right, enantiomers are chiral molecules that are non-superposable mirror images. Okay. So that means if you take the mirror image of the molecule, you will not be able to overlap it with the original structure if they are enantiomers. All right, and a feature of enantiomers is that all the chiral carbons on that enantiomer, on the original structure, will be the opposite if we take the mirror of it, if we look at the other enantiomer. Okay, so let's draw here an example. All right, so we have this. All right, so we have this structure here, right? So what we're going to do is we're going to look at the Rns configuration on it. So first, let's identify the chiral carbons here. So let's start by looking at the left one right here. Is this carbon chiral? Well, there are two hydrogens on it, and so these are not four unique. That doesn't make those unique substituents, and therefore we can't look at that carbon. What about this one right here in blue? Well, it has a methyl, a hydrogen, an OH group, and some other carbon chain with other substituents coming off of it. So that's four unique substituents. It's sp3 hybridized, and it's also tetrahedral, and so that fulfills those requirements. And so now let's try to number our priority. All right, let's try to determine the priority groups. So if you want to pause this right now, feel free to do so. All right. So our OH would take the most priority, number 1. This carbon chain over here would take the second priority, this one here, because it's connected to a chlorine. It's connected to a chlorine and two hydrogens, right? And so if we want to compare between this carbon, well, that carbon is only 3 hydrogens, so it's not going to be as low. Is not going to be as or higher priority, I guess. So that's going to be our number 3, and our hydrogen here is number 4. Okay. Now let's look at which of the 3 scenarios we have here. In this case, our lowest priority group is dashed, so it's our easiest scenario. We can just draw an arc from 1 to 2 to 3, and we say if it's clockwise, it's because it's moved clockwise, it's going to be the R configuration. Okay, and so I'm just going to erase the stuff here to give us a little bit more room. All right, so let's just write R right over there. Now what I'm going to do is I'm going to take the mirror. Right, so imagine, so here's our mirror. And so let's draw out the mirror structure. Also, sorry if you guys are hearing a little bit of noise. I'm filming this in the HSC library, so you might pick up on some side conversations. Okay, so we drew our mirror structure, and now let's look at our, let's reevaluate our chiral carbon. All right, that's going to be this one right there. Our priority should be the same. We didn't change any substituents or anything like that. So 1, 2, 3, and that's going to be 4. Right, we can, because our 4 is again dashed, we can just cross that out, draw the arc from 1 to 2 to 3. This is going to be counterclockwise, equals S configuration. Okay? And so what this shows you, there's a pattern when we talk about enantiomers. Alright? It's the fact that if you compare 2 molecules that are enantiomers, all of their chiral carbons will have opposite stereochemistry. Okay? So this is a trick you guys can use. If they give you 2 molecules and ask you what is their relationship, are they enantiomers, diastereomers, are they the same molecule, right? Instead of trying to use a model kit or maybe try to use draw on paper ways to show them overlapping, right? Because if they are enantiomers, you will realize that you will not be able to overlap them if they're mirror images, right? What you can just do as a shortcut is just determine the Rns configuration. because enantiomers must have all of their chiral carbons must be opposite configuration. So, as an example, if we had a molecule with 3 chiral carbons with this configuration, RRS, okay, and we have its enantiomer, at those same carbons, it will now be SSR, okay? All of them will be flipped. So that is what an enantiomer is. Now let's move on to diastereomers. Also, this is how you spell an enantiomer. Okay, so let's talk about diastereomers now. So diastereomers are molecules that are stereoisomers, but they're just not mirror images. Okay, and the requirement to be a diastereomer is that you must have at least 2 chiral centers, right? You can't have one. And this is again when we're comparing 2 molecules. And not all of the R and S configurations will be flipped. Like when we talked about enantiomers, all the, let's say, R chiral carbons will turn to S chiral carbons, and all the S will go to R. This is not the case for diastereomers. Okay, so let's draw an example here. This molecule here, and now let's also draw this molecule right here. Okay, and now let's evaluate them, right? You can see that they have the same exact substituents, right? All the carbons have the same substituents on them. They're just oriented differently. And so let's go through the Rns configuration for all of them. So let's start with here and figure out if this is chiral. Well, it has a chlorine, a hydrogen, a methyl, and some other carbon chain, which is 4 unique substituents, right? And so let's figure out the Rns for this. So our chlorine would take the highest priority, followed by this carbon chain here, then our methyl, and then our hydrogen. Now, our hydrogen, which has our lowest priority group, is wedged. So in this case, what we do is we draw our arc, and whatever it normally would be, we just make it the opposite. So cross out 4, 1 to 2 to 3. That looks like clockwise, which would normally be R, but we write it as S. And now let's just clean this up so that we have room for the other carbon. And so that was S. Now let's talk about this carbon. Our highest priority group would be OH, followed by this carbon chain, the methyl, and the dashed hydrogen. In this case, our lowest priority group is dashed, and so we can just draw the normal arc after crossing out 4, 1 to 2 to 3, and that looks like R. Okay, let's just make this here. So we have both of our chiral carbons there. Now let's look at the molecule at the right and determine the chiral centers for that. All right, our priority number 1, 2, 3, 4. Our lowest group is dashed, so this is our easy scenario where we can just cross the 4 out and draw our arc, 1 to 2 to 3. That's counterclockwise, so we're going to write S. And I'm just going to erase this to give more room. Now let's look at this carbon right over here. Let's do our priority again. 1, 2, 3, and 4. Right? Our lowest priority group is dashed, so we can just cross that out and draw our normal arc. 1, 2, 3. That's counterclockwise, so that looks like S. And again, let's just erase this to give us some more room to work with. Now what I want to do is I want you guys to look at our molecule here. Look at all the chiral centers. Okay? The ones in red, you can see those carbons are similar. They have all the same substituents. And so do the ones with blue. They're the similar ones. So you can see, looking at the molecule on the left, the blue carbon, the carbon with the chlorine, is S configuration. On the right, it's S configuration. So we can see it didn't actually change. If we look at the carbon with the alcohol group, it was an R configuration on the left molecule, yet on the right, it became S, so it flipped, right? Similar almost to how an enantiomer works, where a chiral carbon will be the opposite stereochemistry. Yet in this case, we have two chiral carbons, only one of them changed, okay? So this is what it means to be a diastereomer. You have to have at least two chiral carbons, you can have more, right? We can have more than that, but not all of them, when comparing two diastereomers, will have opposite configuration. So we can have, in this case, we had S, R, and here we ended up having S, S. Whereas so those are the diastereomer pairs. If we were comparing enantiomers, we would have something like this. Where all the chiral centers flip, right? You can see that on the enantiomer, this stayed the same, right? Sorry, actually, wait, wrong pair. That stayed the same while the R changed to S, right? And on the enantiomers, all of them changed, okay? And so that's what it means to be an enantiomer and a diastereomer, okay? And so I encourage you guys to practice this. I should have a problem set uploaded soon for you guys. I will try to have it as quick as possible. The ozonolysis and radicals, along with the synthesis problem sets, have already been uploaded, okay? And yeah, so like I said, it's a lot easier to go through Rns configurations when talking about enantiomers and diastereomers than trying to use a model kit or on paper rotate bonds to try to overlap things with each other. All right, so that's what I recommend, is to go straight to Rns configurations. Okay, and so I will see you guys in the next video. If anything here didn't make sense, please feel free to email me. Go to the office hours of the TAs; they're always there to help you guys. And yeah, see you guys in the next video.